Nice. Okay. Yes. Hi. Sorry for the delay. Looks like they didn't have a USB-C port. My Mac only has USB-C, so pain. Anyway, so today we'll talk about Burnside's lemma, which is like it's a formula sort of that you can apply to all sorts of counting problems. I mean, it's very broadly applicable. But the problem is you need some level of like math background to get there, which is sort of on this slide. And I'll try to cover it in as minimal detail as required. Um, but yeah, I mean, plus you need some abstract algebra concepts, but again, we'll try to skip lightly over what we don't need and focus on what we do need. So here's some motivation, right? So here's an easy problem. The sides of a square are to be colored by either red or blue. How many different arrangements exist? Anybody? No. Yeah.
4 squared.
Well, 2 squared, right?
2 squared.
Luckily works either way in this case, but yeah, 16, right? So you have 4 slots, 2 choices for each slot. You're allowed to do repetition. So there you go, 2 raised to 4, 16. Nice. But what is different mean, right? So are these 2 squares the same square or are they a different square? Because if you look at this, I rotated the square on the left by 90 degrees to get the square on the right. So an ordinary person would say they're the same square, but our counting method with like the 2 raised to 4 thing, count these is different. Does everyone agree? Okay, cool. So yeah, on rotation by pi over 2, these are the same. And if we treat colorings that can be obtained by rotation from one another as identical, now how many unique squares can I make? Thoughts? 4. Okay. Anyone else? Well, it's tricky, right? The actual answer happens to be 6. But you just do it case by case, right? And that's not a good way to do things. You have all sides red, all sides blue. One side red, and then you rotate that as many times as you want. That's unique. One side blue, which means all other sides red, right? And then you have adjacent sides blue and opposite sides blue, and the others being red. Right? Again, so this is messy, this is difficult, and doing it on a case-by-case basis as you extend the problem becomes impossible, right? So what if now there are 3 colors? What if I turn this into a hexagon? What if I get a cube that I want to color with 3 colors and then rotate it? It's the same kind of problem, but it's harder, right? And Burnside's lemma does this formally, but this is less interesting than what we want to do, which is we want to count distinct objects up to some sort of equivalence relation, right? And that equivalence relation comes from rotations or reflections or something like that. So does the problem we're trying to solve make sense? Which is I want to count stuff, but I want to treat some versions of that stuff, of that object as equivalent to each other, right? So that's the equivalence relation. Questions? So far, no. Okay, cool. So until now, the only way to do this, like without Burnside, one of the only ways to do this is to just do a case-by-case count, which is bad, right? So yeah, you can take into account some kind of symmetry. That's what, if you're not sure what an equivalence relation is, it's just some kind of symmetry of the object. Okay. Groups. So we'll cover the math background now to actually get to Burnside's lemma. So initially it'll seem like everything I'm talking about is completely unrelated to the problem that I just gave, but we'll get there. Okay. So groups. A group is a set. It has a certain binary operation, which that's the dot out there that showed up not as well as I hoped, but it has the following properties. Okay. First, it's closed. So if I take some element in the set G and another element in the set G, and I operate on them, right? That product, that the result of this operation is also in G. So it's closed, right? It's associative. So everyone knows the associative property. Eventually, this will turn out to be important, as you'll see. Existence of identity. Okay, so there's a unique identity. There's a unique element in G, such that when I operate it with any other element of G, I get back that element. Okay, that's the identity. And there's an inverse, right? So from an identity, naturally you get an inverse, which is for all A in G, you have this A prime. We often represent that as like A raised to -1 sort of, but there's no concept of powers yet. Okay, if powers here would be just like iterative multiplication, but anyway, A times A prime is just the identity again. So questions about these four properties, this is what you need to have a group. So if you can think of any set and any binary operation, right? And what's a binary operation? It's a function with two arguments, right? That fulfills these four properties, you have a group. So can anyone think of examples of a group? You've definitely seen groups before, right? So here's an example, the group of integers under addition. It's also commutative, right? Groups are not necessarily commutative. This one is, so we call it an abelian group. So why is this a group? Well, take two integers, right? Take like 4 and 5, add them, you get 9, which is another integer, that's closure. Associativity, like addition is associative, so we know this is, what's the identity for this group? Anyone? 0, right? 0 is the identity. You add 0 to anything, you get that same thing back. How do you get an inverse in this group? Like what's the inverse of some a in z? It's minus a, right? So a plus minus a is 0. Here's another group, the group of rationals over addition, right? It's very, very similar, right? And you can generalize this a lot, but we're not going to. The group of integers modulo n under addition is an abelian group also, right? What does integers modulo n mean? It means I take two integers, let's say I'm working modulo 7. I add 4 and 4 modulo 7. That's 8 mod 7, which is 1, right? So again, this thing forms a group, right? Because it's closed and addition takes care of associativity. The identity is, again, 0. And to get inverses, you take n minus a mod n, where n is your modulus. Okay. So anyway, there's a group too. Is this a group? C here represents the complex numbers, or the complex numbers over addition a group. Anyone? Everyone knows what a complex number is, a plus ib, where I is the imaginary unit. Yeah, cool. It's closed, really. Is there an identity? What's the identity here? It's the same, 0 plus 0i. How do you find inverses? It turns out to be the conjugate, I think, right? Anyway, you can find inverses, not a big deal, okay? Are the integers over multiplication a group? Thoughts? Yes, no. How many people think yes? How many people think no? Okay, most people think no. Why? No inverses, right? So what's the inverse of 2 in Z under multiplication? Well, I mean, over the reals, it's 1 over 2, but 1 over 2 is not an integer, right? Is this a group? Because now I have 1 over 2 as well, right? What's Q? Oh, sorry, yeah. Q is the set of rational numbers, so all fractions. No irrational, so no pi, no e. But yes, any integer divided by any integer would be a rational number. Is this a group? Yeah, actually it's not, because the problem is 0 doesn't have an inverse, right? There are all sorts of edge cases here, but yeah, 0 doesn't have an inverse because in a fraction, your denominator can be 0, right? So this is a group. Sorry, the first one is the group. If you take out 0, you enter a group, right? Because you don't actually need 0 because you're doing multiplication. So your identity is 1, right? So you don't even need 0 here. Make sense? Cool. This is much, somewhat harder. It depends on your, I guess, number theory background, but is this a group? And what are its elements? This is called the multiplicative group of integers modulo n. This is like very closely related with this thing called the torsion function, right? So if you actually want to turn this into a group, what you have to do is you have to take all the integers up to n that are co-prime to n. And if that's a prime number, that's just all the integers till that prime. And then that thing forms a group under multiplication. Why, how, they're not interesting, you can look it up. It's a very clean sort of, if you're able to understand that group, you sort of got the sense of what a group is. But again, that's like something interesting you can look at. Okay, before I move on to symmetry groups, questions about just groups in general. Anybody? Set with an operation fulfilling certain properties. It sounds complicated, it's just not. Right? Check each one of those properties, check. Basically, the actual way to check is to check each one of those properties, and some of them you have to check for every single element because there are lots of for alls there, right? But in general, like we figure out most of the easy groups, so we're good. Okay. Symmetry groups are interesting because these, until now we've been talking about groups over like sort of numbers that you've seen before, but symmetry groups sort of will generalize this notion a little bit, or they'll use the general form of a group. So this is what a symmetry group is, which again is not interesting. Let's talk about some intuition. Consider two squares. right? They're part of the same equivalence class if, right? Again, going back to our old thing, if you can get them by using rotation, reflection, translation, or some combination of the three, it's still the same square. Let's say, right? This is the equivalence relation we choose. Make sense? Okay. I can get to a translation because like I'm not actually working with coordinates or anything. So it's rotation, reflection, and a combination of the two, right? Questions about this. So does everyone understand what are like how we're considering two objects equal in this scheme? Cool. So here it is visually, and this looks a bit involved, but it's not that bad, right? So the first one is just I keep the square. The second one is I rotate it by 90 degrees clockwise, right? So 1 goes to 4, 2 goes to 1, 3 goes to 2, and 4 goes to 3. Does that make sense? That's what that rotation is. R2 is just rotated by 180, and then you can see how each vertex maps. R3, FB is vertical reflection, so that means I reflect it like that, flip it across a vertical axis. I can do horizontal reflection, diagonal reflection, and counter-diagonal reflection over the diagonal that leans backwards, right? So this is the set of symmetries, right? I mean, this is sort of, why did I choose these specific operations? I mean, I could have chosen something else, but as it turns out, this set is a useful set. And we'll see why in a sec, but these sets of symmetries, they're actually bijective functions, right? That look like this. ID, which is the identity transformation, just maps the vertex 1 to the vertex 1, 2 to 2, 3 to 3, and 4 to 4. Whereas FD, which is like flipping along the forward leading diagonal, it swaps 1 and 3 basically. So as you can tell, this is a permutation if you're familiar with the language of permutations. I don't think of it as just some bijective function. Yeah. So this set I was talking about earlier is a set of bijective functions. Yeah. Questions? Cool. So yeah, again, what's the group operation though? So I have a set of these functions. I'm going to say these are the elements of my group, right? But what's the group operation? Well, what we really want is function composition, right? That's because I can apply one thing, then I can apply another thing. I can rotate it, and then I can flip it, right? That's why this group has the operation of composition. So it means do this bijective function, then do this bijective function, which is composition, right? Do one function after another. Okay. For instance, yeah, here it is, right? So again, this is a little weird because you do R3 first and then you do FH in this notation. You can look at it the other way. Different books choose different things. I like the one where you go right to left. So this means rotate by 3 pi over 2 and then reflect across the horizontal. And it turns out that this is equivalent to FD. And as it turns out, we need closure, right? But this thing is closed. It is closed. Function composition is associated, so that's good. What else? You need an identity. We have an identity that's just ID, right? You need inverses, and it turns out you can, some of them are their own inverses. So like FD, FB, FB, like those are their own inverses. You just flip it twice. And rotation naturally has an inverse. You rotate by 90 degrees clockwise, rotate by 270 clockwise, and you'll be back and so on, right? So the inverse, so can everyone see there's an inherent group structure in this whole thing? Yeah. So I know the hardest thing to believe is that this is closed, right? At least it was for me. There's a way to actually prove it. An easy way to do it is to just write out an n by n table, like here the 8 by 8 table, and just actually compose them and try. That's called the group operations table, and you can write that out. And you'll see that you can frame any composition of these as one of the elements of the set. So that's closed. Yeah. Is it abelian? Very important question. So if I apply a rotation and a reflection of some sort of versus a reflection and a rotation, will I get the same thing? No, it's not commutative. It's not abelian. Okay. So cool. Here's some examples of symmetry groups. You have cyclic groups which consist of all rotations by multiples of 2 pi over n around a point. And order means the cardinality of the underlying set of the group. Okay, that's how you can think about it. The Cn over here, for instance, like C4 would be all the rotations of a square. C5 would be all the rotations of a pentagon, and so on. Okay, and then you have the dihedral groups. There's some messy notation here where some people represent what I call Dn as D2n because the order is 2n, right? But we'll call it Dn because it talks about it. It can be thought of as the symmetry group of an n-gon. Okay, So anyway, there's all the rotations in CN along with reflections along all the n axes passing through that central point. Okay. And again, I'm framing this very much in terms of an n-gon, but these groups are more general. You can apply it to rotate anything, right? It's just easiest to see these axes and the rotations and stuff when you think of like a polygon, right? Okay. And why is the order 2n? Because you get n rotations in Cn and n reflections overall. So you get n plus n, which is 2n. And that's called Dn, okay? And the group we just looked at was D4, right? It's all the reflections and rotations of foregone square, right? And there are many, many more, right? There are lots of symmetry groups. I mean, we just looked at very simple two-dimensional ones. You have three-dimensional ones, which are way more complicated. Even two-dimensional, they're even more. There are these groups called wallpaper groups and other things that have different forms of symmetry. Because your symmetry just doesn't have to be reflectional and rotational, right? There are more ways to have symmetry in objects, right? And like, yeah, I mean, there are more groups, but these are the ones we focus on because these make it very easy to see Burnsides visually, okay? Now let's talk about actions. Okay, before this, any questions? Because actions goes into the hardest math field, most likely. No? Oh, cool. So a group G with an identity E can do this thing called act on the set X, okay? It can do things to a different set X. So a group is there, it has its own operation, has its own set, but it can act on another set X, okay? And this other set X has to only fulfill like two sort of properties for this group action. So again, the group action maps G cross X to X. So it's alpha is a binary operation, right? That takes one input from G, one input from X, and gives you an output in X. Okay. And what does this actually do? This says, well, if you do, what are the two properties it says? Well, if you do alpha on the identity element of the group and you operate that with any element in X, you should get back that element of X. So that means the identity in G is also an identity for X. All right? Making sense? And now the second one looks pretty bad, but I'll explain this right after I switch up my notation a little bit, which is we often write Gx instead of alpha Gx. Okay? So then it becomes much clearer what the second thing is. The second thing basically says if I do G on H of X, I can do GH on X. That's all it's saying. Okay? So if one of the group elements G acts on H of X, I can also write that as G of H acting on X. All right? Yeah. So again, these will have some outputs and exits. Nothing too much to worry about. Okay? It's just using the group operation. By the way, when I write Gx, that means G dot X, where dot is the group operation. That's how we use the group operation. Okay? Questions about this? This will become clearer in a second. You'll have to work with this a little bit. I know it seems like a very synthetic definition, but I'll explain a little bit more about why this is here. Okay? So what are G and X? Well, in our case, G is the group of all the symmetries, and X is the set of all the possible colorings of the square, right? So if I take a coloring and I rotate it to be another coloring, you see how the symmetry group is acting on all the possible colorings. So you take all 2 raised to 4 colorings, and the symmetry group acts on it by rotating it, reflecting it, whatever. And then we sort of take a deeper look at this group action, and we analyze the function alpha a little bit more, okay? To see like what its structure is, because is alpha bijective, is alpha surjective, is it injective? It's hard, right? So we'll think about those properties, and we'll better understand how many of those like symmetries cause it to map to the same thing. How many of those colorings mean the same thing? Okay, so that's the big idea here, which is G is the group of symmetries and X is all the possible colorings. You try to categorize those colorings based on how G is acting on them. That's why we need groups and group actions. So, for instance, here's one possible coloring of the square. So there's an element of X, right? That I'm applying an element of C4 on right now, which is rotate by 90 degrees. Yeah. So there's a reformulation of the same thing, but with more math, I guess. Questions about this, like why, what is X and what is G and why are we doing it? Well, why we'll get to, but like, how is this even working? No, it's just a transform, right? It's all just functions. So what's a fixed point? Now that we have functions, fixed points are very natural to talk about. It's some x in x, right? Such that action by G leaves it unchanged, right? So the set of all fixed points of G is all the x's in x that cause operation by G on them to leave them unchanged, right? So it's the set of all x that sort of G can't change, where G is one of the group members. And again, if you think in terms of symmetry groups, what is this saying? What is it actually saying? This is saying, well, if G acts on this coloring remains unchanged. Yes? Right? So the identity thing is like, if the group element G here is the identity, what's fixed G? It's just all of X, right? For instance. Yeah. And so on. So we'll think a little bit more about this. But overall, it's just all the elements in X that are completely unaffected by G. Right? It's the fixed points. What's an orbit? An orbit is the set of elements to which you can move X via action by G. Right? So basically, it's if you take G and X, it's just all the Gx. Orbit sounds fancy. It just means this is sort of this is where X would go if I operated on it with every element of G. Right? So take G1, take G0, operate on X. You get XG0. You get G0X, sorry. G1X, G2X, G3X, G4X. That's this set. Okay. So again, it's nothing super special. All right. And orbits partition X. Now, this is interesting because there's no sort of reason that you'd expect them to do this. But if you take like all the things that X can go to, right, and all the things that some other Y goes to because of action by G, those are completely separate. It partitions that set. In fact, if you take all the orbits, you get a partition of the entire set X. Why? Well, let's think about it, right? So let there be like sorry, X prime is not the inverse. So let there be like some X prime in G of X, right? So that something else be in the same orbit as X, right? But let it have its own orbit that is not equal to the orbit of X, right? So that means there's at least one element that is outside. So if you think about the Venn diagram, there's one element that's like outside G of Gx, right? So let that element be Y so that it belongs to G of X prime and not Gx, right? So Y is like, obviously, how did we get Y? We got it by, doing some G1 on X prime. That's the definition of an orbit, right? But X prime itself is a part of the orbit of X, right? And since X prime itself is a part of the orbit of X, we can write it that way, which is there's G2 times some G2 times X, right? But that means Y is G1 times G2X. And you see, this is where all those properties become useful. No. Okay, whatever. Where I can sort of, I can basically turn G1 times G2X is G1 G2 times X, which means Y is actually in Gx. So the orbits partition the same. The proof isn't important, just the idea that the number of orbits concept makes sense, right? Because if you partition a set, the number of partitions is actually a quantity you can think about. Whereas if you just have subsets that possibly overlap, it's not as clean a number to talk about. But the orbits actually partition X. So there's a number of orbits that X has under action by G. Yeah, following sort of. So we're able to partition X by acting on it in different ways by G. Okay, that's the idea. And what we really want to do is count orbits. Think about it, right? So X is the set of all possible colorings. This is acted on by G, which is some sort of symmetry group, right? And consider the orbit of some X in X. Well, all the elements in this orbit were reached by rotating or reflecting X in some way, which means they're all really the same coloring. So everything in basically one orbit represents one color, one unique coloring, down up to rotation and reflection, which is exactly what we do. So the total number of orbits is the total number of unique colorings with that symmetry constraint. Makes sense? A little tricky, but this is the big picture of why we need that orbit thing, right? It's because each orbit uniquely corresponds to one unique coloring down to what our group says uniqueness means. Right. Question? I know it's a lot, so like take some time to digest it. There's like a lot of vocabulary, and I'll keep like re-explaining what an orbit is and like other stuff like fixed points and all of that. We'll keep coming back to it. But this is the big idea, is why we want to count orbits. And Burnside's lemma is just a thing that counts orbits. It's just a formula for the number of orbits. Okay. So here it is visually. This is the set X, and I showed you graphics from a YouTube video, but whatever. Right. That box represents the orbit of X. X star is something that you could get to by rotating or reflecting X. And that yellow box I've drawn is all the things in this orbit, but all of those are one unique color. Yeah. Yeah. One last thing before I move on, stabilizers. It's very closely with the fixed points. It's just all the G in G that leave X fixed. Okay, so the stabilizer of X is all the things in G that were unable to move it. Okay, and contrast this with the fixed points, which is sort of the other way around, which is all the things in G, or all the things in X that G couldn't move. So it's all the things that couldn't be so that's the X that couldn't be moved by. It's the set of all the things in G that couldn't move X versus all the things in X that G couldn't move. That's the difference between a stabilizer and a fixed point. They're similar. It's just one works on the image and one works on sort of the domain. Right? Okay. So line up the elements of X. Here's a visual proof. Right? This is very nice. I still have to use this. This is the proof. I still have to use something called the orbit stabilizer theorem, which is tricky, but we'll get there, right? So again, the same color means the same orbit. So how many orbits are here? Anybody? Three. Oh, three orbits. Right? Very nice. Now what I'm going to do is I'm going to draw the group G, and I'm going to draw a line between an element of G and an element of X if operation by G on that X leaves it unchanged. All right. So those are these sticks, right? Here. Spaghetti. What do you think this first element is? Can anyone guess which element of G does that look like? Well, it looks like it's connected to every element of X, which means it leaves every element of X unchanged, which means which element of G is it? Sorry? It's the identity, right? It doesn't do anything, so it's connected to all of them. There's the other ones are connected in whatever pattern they are. Note that this is just a pictorial representation. This is not an actual group, it's not an actual set that is there. It's just to like show you how Burnside is good. Okay? So the goal of this is a counting argument, which this ties really nicely back into combinatorics because counting arguments are very, very common. So what we're going to do is count the number of spaghetti. Okay. Yeah. So there are two ways to count this. It's using the number of outgoing edges from the top nodes or the number of incoming edges for the bottom nodes. Those are the two counting things we'll do and then set input. Okay. So here are the top edges, right? These are just the numbers, but more formally, what is the fix of G? It's all the X in X, such that G of X is equal to X. So what we have to do is we have to sum up the fix for each of these elements, right? Nope, sorry. Yeah. So I have to sum up that the fix of this element in G is 10 because that's the identity. The fix of this next element happens to be 1 for whatever reason. But what I have to do is I have to sum up the sort of the cardinality of each fixed set, right? To count the top. So does this formula make sense to everybody? It's just basically adding up the number of outgoing edges from each G. And the way we write that is the fix, right? Yeah. What about the bottom? The outgoing lines or incoming, depending on how you look at them. I guess incoming makes more sense. From each X, right? So this is tricky, but remember the stabilizer, right? The stabilizer says, well, it's all the G in G such that G of X is equal to X, right? Cool. So all the X in the same orbit have the same number of stabilizers. Why is that? You can prove it, it's not hard. But if you're in the same orbit, you will have the same number of stabilizers. It's another theorem, it's a lemma, it's a short lemma to prove, not hard. But anyway, the total number of outgoing spaghetti from an orbit is the number of stabilizers of X times the number of things in the orbit, right? Because each thing in the orbit has the same number of stabilizers. Multiply that by the total number of things in the orbit, and you have basically the number of outgoing spaghetti from a single orbit. What do you multiply that by? The total number of orbits, right? So this is going to be the number of orbits that times the number of stabilizers, which by the orbit stabilizer theorem is just the number of elements in the group overall. This is not obvious to prove, okay? There's a nice, elegant visual proof of this that I'm going to omit, but you can prove this, right? There's some intuition behind it too. It's sort of, again, you can look at fixed points and you can look at how you get from one place to another. But anyway, this is all G now, right? So each orbit has G incoming spaghetti, right? And how many orbits do I have? Well, number of orbits. So number of orbits times G is the sum of the cardinality of the fixed point for each element G in the group. And to get the number of orbits, which is, remember, what we wanted to do, I divide both sides by the cardinality of the order of G. And this is Burnside's number. It's a little tricky. It's a little tricky getting there. We'll use it a couple of times, and hopefully that will help it make more sense. But any questions so far about like the proof? I know it's like the spaghetti sticks and all of it make it look simple, but it's pretty involved. Sort of fix is a notational convenience, sort of, right? And orbits also, you can think of them in this proof as a notational convenience, but they're useful because that's what I really wanted to count, right? And this gives me a formula to do it. So if you look at this formula and think about it for a second, it's not as clean as we'd like it to be, because you still have to go through each element of G and figure out what its fixed points are. So it's not a very clean formula, but it is cleaner than doing it by cases, right? And this is the best we have, okay? There are generalizations of this. There's Polya's enumeration, which is more complicated, it looks more deeply at the structure of the permutations, and permutations have this thing called an order, right? So cyclic permutation has this thing called an order, which is after how long does this permutation just go back? After how long does it pick up? How many iterations of this permutation do I need before it's the same as the identity permutation? And Polya's uses that to generalize this idea further beyond, just having, beyond just looking at this single group. It basically lets you use a generating function and do more complex things. But this is sort of the easiest form of doing this sort of enumeration when you have equivalences. Here's some examples. So here's the original example. We'll try solving it now. Does anyone remember what the answer was? It was 6, right? So let's see if this thing gives us the same answer. So again, colorings that can be obtained by rotation are identical. So which symmetry group is this? Anyone? Does anyone remember the two kinds of symmetry groups we talked about? So which symmetry group is rotation is identical? Anyone? It's C4, right? The dihedral group would treat reflections as identical, which this problem doesn't want us to. So it's C4. And the cardinality of G or C, whatever, is 4, right? Because it's a cyclic group, there are 4 possible rotations. Identity, rotate by 90, rotate by 180, rotate by 270, right? Those are the rotations. And now we want the fixed points. So under the identity, right, each coloring is unique. Yeah. So all the possible squares are unique. We knew this. What about R1? We want squares that are like invariant under rotation by pi over 2. These are our fixed points, right? These are exactly 2, which is all sides red and all sides blue. Because if you rotate these, they don't change. That's the number of fixed points, right? These don't change because of rotation by 90. Rotation by 3 pi over 2 is similar, right? Because if you have even one side color different or two side color different, if you rotate it by pi over 2 in any direction, look, 3 pi over 2 is just negative pi over 2. So it's the same logic for R3, right? Which is that the only squares that are invariant under this operation are all sides red and all sides blue. Do these two make sense? This is where the reasoning gets straight, right? Which is how do you actually think about these fixed points? Because you have to think about the group's action on the set. Yeah? So those are invariant. And rotation by pi. So for these to be invariant, opposite sides must be the same color, right? So we get 4. How do I get 4 out there? Anyone? No, fine. No, okay. Well, the way we get 4 is the following, right? The opposite side must be the same color, which means if I take this and I flip it over, right? The opposite sides, these two sets of opposite sides must be the same for it to look the same once it's been like turned by 180. So that means I have the square red, red, blue, blue. I have the square blue, blue, red, red, and I have all red and all blue. That's 4. Yeah. And you can look at this 2 squared also if you think about it with a little bit of the usual sort of, you know, filling in the boxes method from combinatorics. But let's actually apply Burnside's. There you go, right? So you take 16, which is the number of fixed points from the identity. You take 2 and 2, which are the fixed points from R1 and R3. You take 4, which is the number of fixed points from R2, and then you get 24 over 4, which is 6, which matches our 24. Yeah. So we were able to count sort of the total number of orbits, and that corresponds directly to the number of unique colorings up to the symmetry enforced by the group features. And again, if you choose D4, you'll get a different number, right? Because now you're treating reflections as the same. So can anyone guess, will the number be smaller or bigger? Well, I'm treating more things as the same, right? So it'll be smaller. Yeah. Okay. This is the hard one. Burnside's on the cube. So you want to color this cube with 3 total colors, right? Red, green, blue will do fine. And the backs are also colored. This is like one view for the cube. And here is the case here. So if you actually want to do this without Burnside, down to rotation, right? This is a lot of cases. Like our square was easy, it was just 6 cases, right? Even doing it raw case by case, and Burnside's was 4 cases. So 6 and 4 don't seem that different. Think about doing this by cases. Okay, it's very, very tricky. It's very, very messy. It's difficult, right? You can try if you want. The bottom line is you'll get a lot of cases. The final answer works out to be 60-ish. It's 57, I think. But anyway, so the group is this is not a group I've taught you because this is a 3-dimensional case. But this group has 24 elements, and these are sort of the rotations that are relevant. Okay, so the identity mean is 3 raised to 6. Why? That's because I have 6 possible slots, right? 6 possible faces I want to color, and I have 3 choices for each of them: 3 times 3 times 2 times 3 times 3, 3 to the 6. That's the identity, right? And I have all of these differently colored things. And does the identity make any of them be the same? Like, are any of them invariant under the identity? Well, all of them are individually invariant, right? What about rotations by pi over 2? If you think about it, if I like take this cube, I wish I had a Rubik's cube, but if I take a cube and I make an axis vertically through it, so through the top face and the bottom face, then I want to rotate it by pi over 2, right? The only cube that's actually going to be invariant this way is if all the lateral faces, i.e. the front, the back, the left and the right faces are all the same color. Because this is the same argument as the square, right? But now I have 3 possible axes and I have 3 possible colors, right? And so again, 3 possible colors. So go back to the original case. I have to choose a color for the top, a color for the bottom, and a color for all the sides. So that's 3 raised to 3, right? But I have 3 possible axes. So multiply 3 raised to 3 by 3. And then I can account for like 3 pi over 2 as well, because it's just minus pi over 2. It's the same logic. So I just multiply this by 2 over 2. You can do this as a separate case if you want, but I don't. Okay? Cool. And when I do pi over 2 rotations, I mean, I know that this is not 24 bullet points, because when I say rotations, I'm counting like that rotation and another weird rotation, and then moving around the axes. All of those are separate elements in the group, but we analyze them conveniently this way. Okay, what about pi? Again, very similar argument to the 180 rotation of the square, where you get uniquely colored lateral faces. So you're rotating by pi. So you have to fix the top and the bottom can be whatever color, but you have to fix the left and the right and fix the front and the back. Right? So you should get 3 raised to 4, and you get 3 possible axes. So 3 times 3 raised to 4. Rotation is about 8 diagonal axes. These are the ones that pass through the corner. So you can rotate a cube using like an axis that goes through a full diagonal. This is the axis that corresponds like for a unit cube is the length of √3. Okay, that axis. And you have 8 of those axes, and each corner fixes a color. If you think about it, just visualize this a little bit, you'll get there, right? And like if you have a corner and then I want to rotate it for the thing to still be the same, right? That corner will just have to fix all the three faces that touch it, right? So that means that I can select. I need to select a single color for one corner and a single color for the other corner, basically. So that's 3 squared, right? And I multiply that by 8 for each of the diagonal axes. And then I have rotations about the edge midpoint axes. So again, there's another kind of rotation, whatever, right? Like you can work it out. It's not interesting to walk through. The interesting part is the answer, which is this. You can just plug it into Burnside's. And this works out to be a pretty big number, right? So it's 57 times 24, say 1500-ish, right? It's a big number. So again, analyzing cases hand by hand is very, very painful. But we boiled it down to what the identity cases triggered. So we just boiled this down to 4 cases that we had to think about for a little bit. And we got our answer. So that's it. This is the YouTube channel I got the graphics from. Does anyone have any questions? I was supposed to keep this a little short because there's a lot of content. There's a lot of examples. I'll send a list of just problems you can apply Burnside's and the more general version Polya's to. And it's a list of like, just on stack, there's a list of like 400 problems at least. Right? So it's very, very general. And it's a useful result that sort of is pretty mathy, but I think it's interesting. So, question? Yeah.
What classes would cover?
417 covers Burnside's. There's a 500 level combinatorics course that covers Polya's because it's Polya's uses like generating functions and stuff that's more combinatoricsy. So 417 is good for that. But yeah, Math 417 will cover Burnside's. To get more general version, it's the graduate combinatorics course, I think. Yeah, I think it's one of those. I don't remember which one. Like 5. I think, yeah, it'll be the algebra combinatorics course, whichever one it is. Other questions? So hopefully it was clear. Again, the sort of the key idea that hopefully you should walk away with is counting. We sort of took groups and made the fundamental problem of counting the number of, we sort of tied the problem of counting the number of orbits of a group to basically the number of total, unique objects that we have. And we did this by using the group relation, right? Which sort of tells me what objects are going to be the same and which ones aren't, right? So lots of like other places to go from here. You can read more about symmetry groups. You can read more about groups in general. You can read more about like Polyas, which you don't need much more group theory for Polyas. There's all group theory. Polyas will require understanding permutations better and generating functions. So those are the other places to go. Yeah. All right. Thanks for coming, everybody. I think that's all I have. Does Zoom have questions? No. All right. Cool. We are done.